Okay, so I get start my talk, and I'm Kohei Yoshimura from Physics Department of the University of Tokyo. Today I'm going to talk about fluctuation and thermodynamic continuations in deterministic chemical reaction networks, mainly based on this paper. After this paper was posted on the chat, in fact. And also it is related to this preprint, we submitted yesterday and appeared today. And we consider general chemical reaction networks like this and draw labels, reactions, reversible sets, reversible pairs of reactions, and mu and nu prime are the stoichiometry. And the dynamics is described by the deterministic rate equation. Here, C is the concentration and alpha labels the chemical species from 1 to n. And K-rho and K-rho are the reaction rates of forward reaction and backward reaction, and which are usually in general nonlinear functions of concentrations. And so the theoretical frameworks of this deterministic chemical reaction networks and stochastic jump processes resemble each other, as you may know. And approach based on this analogy has worked very well, especially to understand the chemical reaction network side. And so, for example, we can consider Schneckenberg theory or information thermodynamics like things in chemical reaction networks. And please see also this paper where we derived some tighter theories or many things integrating to frameworks, by the way. So let me show the similarities by defining some important quantities in this talk. First, there are equations of motion resemble, and here is a chemical reaction rate equation, and C is a variable, the concentration, and S is a stoichiometric matrix defined by mu prime minus mu, and J is a reaction current, which are given by the difference between the forward and backward reaction rates. And on the other hand, this is a master equation for jump processes, and here the variable is B, the probability, and B is the instance matrix of the directed graph of states and transitions, namely the graph whose knows the states and H is the transitions. And it is given by like this. So B is 1 if the I, the H and the I, and minus 1 if the H starts from I, otherwise 0. And J is a probability current, which is given by using the transition rate, K. Also, the thermodynamic structures are similar to each other. And by assuming the local detail balance relation, the affinity or the thermodynamic force are given by the log of the ratio between the forward and backward fluxes. And the entropy production rate given by the product between J, the current and force, also have the very similar forms. So there is a difference, huge difference, namely one is fluctuating and the other is not. In stochastic thermodynamics, fluctuations play a central role, for example, in fluctuation theorem or thermodynamic constitutive relations. But fluctuations are absent in deterministic chemical reaction networks. So one question can arise: are there any counterparts of fluctuations that can bring some insights to chemical reaction networks? And the answer is yes. This the diffusion coefficient matrix defined by using reaction rates can play the role of diffusivity in deterministic chemical reaction networks. It was previously known, for example, in this paper, the author discuss the a kind of fluctuation dissipation relation with this diffusion coefficient matrix, but has not been utilized very effectively. And in this work, and also in this work, we derived a TR for chemical reaction networks by using this T, the diffusion coefficient matrix. And in this, the original paper, we derived this inequality by using this relation gives a lower bound for the entropy production rate by using a kind of flow and a kind of fluctuation. And this is refined like this in this preprint. And we can also derive the speed limit, namely a lower bound for the time it takes by using the L1 distance between the initial and final distribution of concentrations and the time average of the trace of the diffusion coefficient matrix and the time integrated entropy production. And then one can suspect why these diffusion coefficient matrix. To this question, we can answer from 2 points of view.
Sorry, you have 3 minutes left.
Okay. And yeah, you can understand this point from analogical point of view. First, in a jump process, traffic defined by this gives a short time fluctuation like this equation, and one can prove a short time TR with this DR. And so if one define a law, a kind of traffic for chemical reaction networks by summing KO and K minus rho, then one can write diffusion coefficient matrix by using this kind of traffic. So this is analogous to the fluctuations in jump process. This is very analogical discussion. And another understanding comes from chemical master equation and Fokker-Planck equation. And as you know, the system expansion of the chemical master equation brings the chemical Fokker-Planck equation, or in other words, chemical Langevin equation. And here, omega is a volume parameter, and F is defined like this, and D is the chemical the diffusion coefficient matrix. So D is the diffusion coefficient of the chemical Fokker-Planck equation times the volume. This is an example of the solution of the chemical Langevin equation. And here, if omega is not so large, the solutions, the trajectories fluctuate. But if one makes omega very huge, then the solution, the trajectories converge to this deterministic solution. Then the fluctuation vanishes. But this T actually encodes the information of the fluctuation that vanished due to the thermodynamic limit. So from this point, one can understand these are kind of fluctuation in a macroscopic level. And yeah, here is a proof of the TR. So I go quickly, and this quantity is written like this. And by regarding this ratio as a metric, then one can use the Cauchy-Jordan inequality. And this metric is also an important point of our preprint, by the way. And by using the logarithmic inequality for this quantity and this A, then one can prove this inequality, the TR. And this is a summary. And also, in addition to the results I presented now, we prove refined tighter bound of this kind of for this excess entropy production rate in this paper. So please check it. And also please check this PRA paper for a bit more details, including the proof of the speed limit. Yeah, thank you for listening.